So, good morning, everyone, and welcome to the Cardiac Imaging Journal Club. My name is Mariana Falcão. I am a fourth-year PhD student here at the CHUV in Lausanne, and I will be our moderator for today's session. In fact, I am coming as a replacement to our in-house moderator, Dr. Aurélien Bustin, who is switching roles today and is going to be one of the speakers. I want to just mention that this session is being recorded. Okay, so today's session is a very interesting one, and it has one main focus in common, which is image reconstructions of highly undersampled multi-dimensional MRI datasets. And joining us, we have two experts in the field, Dr. Jérôme Yerli and Dr. Aurélien Bustin. And I must say I'm very excited to be moderating today because I know both of them, and I've had the pleasure to work and learn from both of them. We can start our session with first Dr. Jérôme Yerli, who is one of our senior research scientists here at the radiology department at the CHUV. He's also a collaborator from the Center of Biomedical Imaging, or as we call it, the CIBM. And his main focus of research is about understanding and implementing advanced multidimensional reconstruction algorithms to resolve respiratory and cardiac motion in multidimensional cardiac MRI. And today he will be talking to us about the basics of compressed sensing and how it works in particular in an MRI context. So without further ado, I pass the word to Dr. Yerli.
Okay, can you see my screen?
Yes, all good.
Awesome. Well, again, thanks Mariana for the introduction, and thank you Aurélien for the invitation and for giving me the opportunity to present this talk. Basically, what I'm going to present today is a talk that I've already gave a couple of years ago at the SCMR. It was an educational talk that I gave for the technicians. So as you will see, I tried to use as many animations as possible and illustration in order to make it a little bit more intuitive. So today I'm going to talk about compressed sensing, and hopefully by the end of this presentation, you will understand, or I will have uncovered some of its magic, and you will understand how we get from this heavily undersampled image here on the left. And with some magic, we then will get to this much better image here on the right. So I'd like to start first by mentioning that most of the content in this presentation is based on the work from Michael Lustig. And I encourage everyone who would like to learn about compressed sensing to start by reading this seminal paper. So data collection with MRI, as you know, is typically performed in a line-by-line fashion, as shown in this animation. And because of that, it is relatively slow. And we basically, with the physical acquisition, we reach some limitation that are both physiological and physical. So if we cannot acquire the data any faster because of gradient by using better gradient, one way to speed up the acquisition is to acquire less data or fewer data and then reconstruct this image on the right from fewer data. But as we will see, then we will need more complicated reconstruction. So we know that most medical images are compressible, which means that after we acquire the images, we can apply some compression algorithm to represent this image with fewer data, and then we can save these images on our hard drive, and this image will take less space. No, the main idea of compressed sensing is, or what we would like to do is, could we actually include this compression into the encoding process of the acquisition? And then, because we know that these images are compressible, then we could reconstruct or use this a priori information in order to reconstruct the images from this fewer data. So this is really basically the main idea, or this is the paradigm of compressed sensing. Now, what is needed for the magic of compressed sensing to happen? Well, excuse me. So compressed sensing has three main requirements. And the first requirement is that the image we try to reconstruct has to be sparse or compressible in some transform domain or in some domain. The second requirement is that the acquisition has to use a pseudo-random or non-uniform sampling approach in order to produce incoherent artifacts. And the third requirement is basically that we will need to use nonlinear reconstruction in order to separate the signal from these incoherent artifacts. So let's start with The first requirement of sparsity. So what is sparsity? Well, a sparse image, as you can see here on example on the left side, is an image where most of the pixels are zeros, and we only have a few non-zero pixels. On top, you can see actually an example, like a synthetic example of a sparse image where all the pixels in the image are zeros, but we only have 4 non-zero coefficients. Now, what is a non-sparse image? Well, I will argue that noise is non-sparse because it is non-zero everywhere, as you can see here. Now, most images required with MR will have basically the signal and some noise in the image. Now, the powerful thing about sparse model is that it is very easy to separate the signal from the noise. So, for example, here we could just apply a simple threshold in order to remove all the noise from the image and only keep the sparse signal. I would like to point out that there are different types of thresholding. So hard thresholding is basically a very trivial thing to do. Here we can see the mapping function of the hard thresholding operation. Basically, it says so X is the input, Y is the output, and it says that all the values below a given threshold will be set to 0. And then all the values that are above the threshold value will be left untouched. As you can see, this can lead to large spurious residual. Another approach is to apply soft thresholding. And the mapping function of this operation is shown here. It looks similar to the one on top, but the difference is that all the values that are below the threshold will be set to 0 again, but all the values that are above the threshold value will be reduced by the threshold value. And these lead to attenuated spurious residual, but we have now a bias, meaning that the amplitude of these coefficients will be reduced by the threshold value. Now I would like to point out that applying this type of soft thresholding operation to this image is equivalent to solving this N1 minimization problem. And this is actually very important, as you will see later. So basically, if you want to solve this optimization problem, which include an L2 norm plus an L1 norm of Y here, this is basically the solution is obtained by simply applying the soft thresholding. So this is super easy to solve this type of optimization problem. And this will become important later. Now, often images are not sparse already in the image domain. And here's an example of a phantom, which is a piecewise constant image. But so obviously it is not sparse since a lot of the pixel values are non-zero. But these piecewise constant images have very sparse edges. So by applying a finite difference operator, for example, we can really sparsify the image. And as we did before, we can now apply a threshold in this sparse domain in order to clean up all the noise. And then by taking the inverse or by going back into the image domain, then we obtain a clean version of the image or a denoised version of the image. No, most medical images are not piecewise constant images, and therefore they are usually not very well specified by finite difference operators. What we can do instead is use a wavelet transform or the other specifying transform that we can use. But here we see an example of a wavelet transform. Now, this wavelet transform does a much better job at specifying the image. And here we can do exactly the same thing. We can see that this sparse domain has a lot of noise. But if now we apply a threshold to remove the noise in this sparse domain, and then take the inverse wavelet transform, we obtain a much better image, like a denoised version of the original image. So we saw that we have different transforms that we can apply in order to specify the image along spatial dimensions, but beyond spatial sparsity, compressed sensing is very good at specifying along time or dynamic images. If we, for example, apply a Fourier transform along time of a series of dynamic images, then we will obtain a very sparse representation where the DC component will have a lot of signal, but then all the other frequencies will be very, very sparse. Another very efficient way to specify the images is along time is to apply finite differences. Here, basically, all the static tissues will be 0, and the only non-zero pixels or data will be where we have physiological motion, basically. Okay, so hopefully now we've understood a bit better what sparsity is. The second requirement is about pseudo-random or non-uniform sampling. So as you know, according to the Nyquist criteria, if you want to sample an image in the frequency domain, there is a certain sampling rate that we need to satisfy in order to capture all the features of the image. And if we do that, then we can simply reconstruct the image on the right side by taking the inverse Fourier transform. However, we want to accelerate the acquisition by acquiring less data, so fewer measurements. Here, this is an example where we only acquire 1 line every 4 lines. And then when we do that, now we obtain coherent aliasing artifact in the image. And when we get this type of coherent artifacts, it becomes very difficult to separate the image from the aliasing. So instead of using a uniform undersampling approach, we could use a radial undersampling approach. No, when we use radial acquisition or radial trajectory, we obtain what we call streaking artifacts in the image that are actually very incoherent, and it is very easy. We can clearly see through these artifacts, and we can much more easily separate the signal from the aliasing artifacts. Instead of radial undersampling, we could also use some kind of random or pseudo-random with variable sampling density approach. And again, this will result in some noise-like artifact, but this is not noise. Again, this is only incoherent aliasing artifacts. But since these incoherent aliasing artifacts look like noise, we can then apply a very similar approach to what we did before with denoising. So again, this is the accelerated image with these noise-like undersampling artifacts. We compute the wavelet transform, and then we can apply some kind of threshold in this wavelet domain as well to clean the image, and then go back into the image domain by taking the inverse wavelet transform, and we obtain this nice image, like a denoised version image. So hopefully now you understand a bit better why we need sparsity and why we would like to have incoherent undersampling artifact in the sparse domain. Now, the last requirement for compressed sensing to be successful is to use a nonlinear type of reconstruction that will allow us to separate the signal from these incoherent aliasing artifacts. The core of compressed sensing reconstruction consists basically of solving this optimization problem, which usually contains one data consistency term, which is this L2 norm, and one or several regularization term, which in this case is an L1 term of the sparse coefficient of the wavelet coefficient. So I've shown an example of a wavelet decomposition. Now, the main idea of compressed sensing is to find or to reconstruct an image M here that will be consistent with the data we've acquired in K-space. But because we undersample the data in K-space, we will see that there are an infinite number of solutions that are of images that are consistent with this acquired data. And compressed sensing, among all these possible solutions, compressed sensing will find the image that has the most sparse representation in the wavelet domain. So before we get into the detail of about this reconstruction, I just want to make sure that everybody understands where this equation or what this equation really means, or where it comes from. And it all starts from the signal equation. So I'm sorry, I'm going back to the basics, and it's probably very clear to everyone, but just making sure that we are all at the same page. Here, this equation says that the coefficient in K-space is position K is simply the Fourier transform of our image. And the position in K-space is controlled with the gradients. Now, because we want to process this signal, so we need to discretize this signal. So we will just replace now this integral with the sum. So this is the same equation as before, but now it is discretized. And what we can do is that, again, this is the equation for one point in K-space at position K. But now if we take all the different positions in K-space and we rearrange these points into vectors and rewrite our equation using a matrix notation, we see that it can be written in a very compact form. So now Y is basically all the measurements that we've obtained in K-space. M is the image we would like to reconstruct. So these are the unknowns. And F is basically of our Fourier transformation matrix. Now, because if we satisfy Nyquist and we acquired the whole K-space, then we can, it means that F will have full rank. And we can easily reconstruct the image simply by taking the inverse Fourier transform. However, remember that we want to speed up the acquisition. So we will undersample the K-space. So we'll only acquire a small portion of the data in K-space. And if you do that, now we will obtain what we call an underdetermined linear system of equation, which means that we can no longer take the inverse Fourier transform to reconstruct the image. Because what happened is that here the number of measurements is less than the number of unknowns. So the image we try to reconstruct still has the same number of pixels, but we acquired much less data. So the rank of matrix is not high enough anymore. So we cannot take the inverse. To understand a little bit better how we can solve this case, we will consider the extreme case where now our nice image here on the right side is actually only made up of 2 pixels. So this is a very simple image made of 2 pixels, and we have the corresponding 2 K-space coefficients. We want to accelerate the acquisition. Here will be by a factor 2. So what we do, we only acquire 1 data point in our K-space. So now we have 1 data point, 1 acquisition, one measurements, and 2 unknowns. If we put that into our system of equations, again, I hope that you can see that these correspond to a line. So these represent a line. The y-axis is m1, so the first pixel in our image. The x-axis is m1, the y-axis is m2, the second pixel in our image. So now we have 1 equation and 2 unknowns. And this basically means that there is an infinite number of combination of m1 and m2 that are consistent with the data we acquired. Now the question is, how do we find a specific solution among all these possible solutions that lies on this line? Well, a popular approach will be to find a solution that will minimize the L2 norm of the image M. And if we do that, basically, we need to use this L2 norm ball. So what we do is that we want the solution to lie on this, to be on this line, and at the same time we want M to be, to have to choose the M that minimizes the L2 norm here. So the L2 norm ball is basically a circle. What does it mean? It means if you travel along this blue line, all this combination of M1 and M2 will give you the same value for the L2 norm. Now you can think of, if you started with the circle at the center and you grow this circle until it touches the line of possible solutions, so where you have the intersection will be your solution of this constraint optimization problem. So in this case, the solution would be, we will have M1 that has a given value, like some values here, and M2 some value here as well. And this is, I mean, that could be a solution, but do you remember we want to find a sparse solution? And obviously this is not sparse because neither M1 nor M2 are 0. So this is not really the solution we want. So what if now, instead of using an L2 norm, we were using an L1 norm? And this is the corresponding L1 norm ball. So again, this looks like a square, rotated by 45 degrees, but this square, again, if you travel along this blue line, all this combination of M1 and M2 will give you the same L1 value. And if you do the same as before, you grow this non-ball until it touches the line of possible solution, where you have the intersection gives you basically the solution of this constraint optimization. And here, this time we have the solution will be M2 will have some kind of values, while M0 is exactly 0. So we get a sparse solution. And this is again what we are looking for with compressed sensing. So this is why people use the L1 norm. Okay, so this is what we call a constraint optimization problem. Now, to solve this problem, usually we have to reformulate it into an unconstrained optimization problem. And for that, we use the method of Lagrange multiplier. Well, basically, you can see this is, here we have these, the data consistency term, which is here, and here we added the regularization multiplied by this lambda. No, we are not going to get into the details, but the concept of proximal gradient descent is, I mean, we usually use proximal gradient descent to solve this problem, which is fairly straightforward. But first, you need to understand that this lasso problem is convex. So basically, there is a minimum. No, the function, so because it is convex, it means that we can define a hyperplane that will bound the lower portion of this graph. So it means this is the lower bound basically for the point at position at M. And basically it means that we are guaranteed that this function will lie above this hyperplane. Now, in addition to this lower bound, the function has also what we call a Lipschitz continuous gradient, which means that it can also be upper bound by a quadratic function. And this is really the idea here. We are trying to optimize, so we are trying to optimize this function f of m, but because of this L1 norm and these two functions here, the L1 norm and L2 norm are coupled, this is quite difficult to do. But instead of solving this problem directly, we can find a simpler problem that is easier to solve. And for that, what we do is that we will find this upper bound. We can do some algebraic manipulation of this equation, and we can come up with an upper bound. And this function g of k, which is an approximation, so it corresponds. I mean, it touches the function fm at this point m of k, and then we are guaranteed that this function will lie above. So it's again an upper bound of f of m, meaning that if now we solve this function g of k that is easier to solve, we are guaranteed to move closer to the minimum of f of m. So what we will do is that we will solve this function that we can easily solve, find a minimum. By doing that, we know that we move closer to the global minimum of f of m. So what we do then at the next iteration, now we have this new position, we calculate again this new quadratic function that will be the new upper bound at this position. And as we will do that over and over, we will slowly converge to this minimum. So this is what is called proximal gradient descent algorithm. So I'm not going to go in too much details, but basically this gradient descent algorithm corresponds to two steps. The first step, if you can recognize that, this term here on the right side is simply the gradient of this L2 norm. And here, this is a gradient step. Basically, what we do is that our position m of k, so this one, is updated by the gradient of the image of this, the gradient of this L2 norm multiplied by a step size. So this is really an update of a gradient descent step, what we call a least square gradient descent or Landweber iteration. Then the next step in the reconstruction process is to solve this optimization problem. And if you remember, this is what I showed you earlier on in the presentation. These may seem a bit complicated to solve, but actually the only thing you need to do is to take your image M and apply some soft thresholding. So this is super simple to do that. And if now you repeat these two procedures, you do gradient descent and then soft thresholding, basically you will slowly converge to the minimum here. Okay, so I think that's enough math. Let's have a look. Maybe we will try to have a more intuitive understanding of how this works. So let's start with our randomly undersampled case-based data here. The first thing we can do is take the inverse Fourier transform to get our first image or estimate of the reconstructed image by filling basically the missing case-based data to 0. Then what we do is that we apply the wavelet transform to represent this image into the wavelet domain. We apply now some soft thresholding to these coefficients to denoise the data. And then we go back into the image space. And now we see we can already get a better approximation of the image. So next, what we can do, so this was the soft thresholding operation. Then what we can do, we calculate the case-based data, and we apply some data consistency. So we could either try to replace the data that we've acquired into this data set, or we can do a gradient descent step like I showed before. Now that we have this new case-based data, and something that you've noticed, we started with the case space that had a lot of zeros. But now, after doing the soft thresholding operation, there's no longer any zeros in there. So what happened during the soft thresholding operation, it means that some of the information got propagated to the case-based coefficient that were not acquired. So now, if we do this data consistency term, go back into the image space and then repeat the process. So we calculate the wavelet transform, apply some soft thresholding to these coefficients, go back into the image, compute the case space, and then apply data consistency again, and we iterate like that until we go to the final, or converge to this final solution. Basically, you will see that we started with an undersampled image, and in the end, we were able to reconstruct an image with very little undersampling artifacts remaining. If we look at it, so this is again kind of the same, just a different representation, so that maybe it would be easier to understand or to see better how the algorithm converges. We have the case space or image domain and our sparse domain. Now, instead of using these images, we will use some in vitro or in silico data. So this is the corresponding case space where the amplitude corresponds to the different values in case space, and the image domain doesn't look like really anything. But the important point is that this image has a very sparse representation in the wavelet domain. Now, if we undersample the case space, meaning that we only keep the coefficients that are in red here, and all the other ones are not acquired. This is an acceleration factor of 4. We see that the corresponding image is very noisy. It looks like it has a lot of noise. And in the sparse domain, we can see as well that it is not sparse anymore. But if now we apply this compressed sensing algorithm, you can see, I will let it go a few times. You can see how it actually converges to, it goes back to this very sparse solution. Okay, so I'm just not sure how much time I have left. Okay, very quickly, I have 2 more slides. I just wanted to show that so this compressed sensing reconstruction is used in our free running framework. So I'm not going to go into details, but this free running framework we uses a 3D phyllotaxis trajectory to acquire data continuously, regardless of the cardiac motion or respiratory motion. But once we acquire all the data, then we use the cardiac signal and the respiratory motion in order to bin the data into different cardiac phases and into different respiratory position. And that gives us basically a data set, a 5-dimensional data set. Now, this 5-dimensional data set is reconstructed with this type of equation. So it's very similar to what we saw before, but instead of having only 1 regularization term, here I have 4 different regularization terms. We have 2 finite differences operator along cardiac and respiratory dimension, and these are what we call these operation, basically these are nuclear norms, and we use them for local lowering type of regularization. So basically this operator M here just takes your full 5D image, selects 1 patch in your image, and then it creates this causality matrix. And then here we do a singular value decomposition. So Aurélien will be talking about that a bit more in details after. But all I want to show here is that we can use exactly this same type of algorithm to reconstruct very complex data. And here you can see an example. We only see the cardiac motion, but these are basically some data that we reconstructed with this compressed sensing algorithm. If you want to get into compressed sensing, the good news is that you don't have to implement everything from scratch, since there are many implementations available online. And here I provide some links for you where you will find some of this MATLAB implementation for the different CS algorithms that exist. And finally, so as a take-home message, so if you want to reconstruct images using compressed sensing, you will need sparsity. So you will need the data. You will need that the data you try to reconstruct has to have a sparse representation in some transform domain. You need pseudo-random or non-uniform sampling in order to produce incoherent artifacts. And finally, you need a non-linear reconstruction in order to be able to separate the incoherent artifacts from the signal. So that's everything, and thank you for your attention. If you have any questions, please, I will take them now.
Thank you, Jérôme, for the great talk. Actually, we are taking the questions, but only at the end of the session.
Okay.
Both of the speakers agree, because since the topics are very correlated with each other, I think it would be a nicer discussion at the end once everyone is presented.
Yeah, sounds good.
We both agree. And if the audience also agrees. So then we can move to our next speaker then, which is Dr. Aurélien Bussin. He's a principal investigator and a postdoctoral research fellow at both the CHUV and the Lyric Center. And his main focus of research is both MR sequence development and image reconstruction, with a strong focus on clinical utility of tissue characterization, pardon me. Today, he will be talking a little bit about high dimensionality patch-based reconstruction algorithms for accelerated multi-contrast MRI. So, Dr. Bussin, the floor is yours.
Thanks a lot, Mariana. I think you can see my slides here. before
Yes,
I start, I think, Jérôme, that was beautiful. I really like your presentation. I think you set the ground very well for the things I'm going to show you now. So today I wanted actually to show you this work on patch-based reconstruction for high dimensionality images. I've been working on this code for something like 4 or 5 years. And that's something you know as HDProst. So that's how we called it in Germany. In Switzerland, we call it HD Santé, but the code is exactly the same. And I'll go into the details of this algorithm, which goes actually one step further than what we see with compressed sensing. So what you see on my slide actually is the Miroir in Bordeaux. And for those of you who are coming in Bordeaux in 2 or 3 weeks, you'll have the chance to see that. And so the motivation behind this work on patch-based reconstruction was originally for multi-contrast MRI and accelerated MRI. Because so for those of you who have spent a couple of time in the scanner or doing CMR experiments, you realize that we collect a lot of images with different contrast. So the images are really nice. You have a very good image quality, but this is very inefficient because all the images are recorded separately. And so at the end of the day, it takes around 45 minutes for a conventional CMR protocol, but it could go way above the hour, depending on the patient. And so you could use accelerated multi-contrast MRI, and that's actually something we do in clinical routine. If you check the CMR protocol you have in your hospital, you would realize that most of the sequences are exploiting parallel imaging or accelerated imaging. So it could be GRAPPA. So in most of the acquisition we perform in clinical practice, we are using GRAPPA with an acceleration factor of 2. Or you could use partial Fourier, or you could use half Fourier as well, for example. And this really reduce not only the breathing time, the breath hold times, but also the entire CMR protocol. But you have still low SNR, so you have to find a way to reconstruct these images, and it's still very inefficient because these images are recorded separately. But you've heard about these very nice technologies, for example, fingerprinting, which I find very exciting. So fingerprinting, the idea behind that is to do a continuous acquisition. We never stop, we never interrupt the acquisition, and we collect many points that we call time points. And we do it by basically varying MR parameters. So this could be flip angles, this could be repetition time, this could be saturation or T2 preparation times. And we run this acquisition for 10 minutes, 15 minutes, 20 minutes, as long as we want. And the idea behind that is that even though the images we collect are highly undersampled, so here I'm not talking about a factor of 2 or 3 in terms of acceleration, but more 100 or 200. So this is highly undersampled, and these are the typical images you will get with the fingerprinting experiments. But since we know the physics behind this sequence, we could use advanced tools such as dictionary matching to really recover the images. And so you could get in one single acquisition proton density images, T1, T2, T1, or whatever you want, as long as you know the physics behind. But of course, we need to reconstruct these images. And so that was the motivation behind HDProst. And there has been a couple of techniques actually that have been proposed to reconstruct fingerprint data sets. And I'm showing you here 3 of them. And the thing behind is that when you acquire multi-contrast images, you have a rich amount of correlated information. So this could be spatially, or this could be in the contrast dimension. You have so much correlation that you could exploit to recover nice image quality. And this is, for example, what multitasking is doing. They build this big tensor by concatenating all the multi-contrast images, and they use tensor decomposition there. Or you could do the same pixel-wise, and that's what we call low-rank inversion or locally low-rank, and that's something, Jérôme, you briefly mentioned. And these are really established technique to reconstruct multi-contrast data set. And for fingerprinting, it's been very useful. But we could go way further if we exploit patch information. So if you take a patch in any image, you're likely to find a very similar patch somewhere else in this image. Do this experiment, for example, on brain imaging or on the heart, you have many similar patches. And so you can exploit that in your reconstruction using this low-rank information. So that's the idea behind HDPROST. So just a little bit of mathematics. And that's an equation we've seen before with Jérôme. It's a very similar equation. You have exactly the same data fidelity term that you see on the left here. Y is the highly undersampled multi-contrast case space that you have collected. X are the multi-contrast images you want to recover. And E is your encoding operator. So usually within E, you have the sampling acquisition, you have Fourier, you have coils, you could add as many things as you want in there. So that's exactly what we've seen before with Jérôme. The only difference is that we have multi-contrast data set here. And so you could use what Jérôme was showing us, the total variation, as a regularization operator to really denoise the images and reconstruct nice quality images. And TV gives, as we've seen, constraints on the edges of the images, right? We want to focus on the images, on the edges in the image. But there is actually another type of regularization, and which is actually even more efficient than total variation. And it is used when we have strong correlations. This correlation could be, spatial correlation within the image or in the contrast dimension. And this is what we call the low-rank regularization, and that's what you see there. And low-rank actually builds on ideas from the theory of compressed sensing that we've seen just before. So if you look at the images on the right there, where the matrix X is obtained by adding noise to a rank 1 image Y, you see this image here is rank 1 because all the lines are similar. And basically, if you look at the singular values of these two matrices, so of course you see on the Y matrix that we have rank 1 because there is only one high singular value, but the matrix X is low rank as well. So even though we have a little bit of noise in there, if you do a singular value decomposition, and if you look at the singular values, you see that there is only one main component, one main singular value, and all the others are basically just noise. And so that's exactly the idea behind low-rank regularization. And so what we want in this type of optimization is to minimize not the total variation, but we want to minimize the rank. Unfortunately, the rank is what we call an NP-hard problem. And so there is very little hope that we can find a global minimum. But there is a solution where we can basically approximate the rank function with some other function, some surrogate function like the nuclear norm. And that's the norm I'm showing you here, which is represented usually with this little star here. And what it is, so the nuclear norm of whatever matrix you put there, a matrix or a tensor, is defined as the sum of the singular values. So it's a real surrogate for the rank function. And so in other words here, with this kind of optimization problem, we want to estimate basically a low rank matrix X from its noisy observation Y. So this is really a denoising problem, as we've seen before. And this estimation is done by truncating, or what we've seen before with your hard thresholding, the singular values of Y. Okay, so that's the main optimization problem we want to solve. Now the question is, what kind of low rank matrix we are gonna put in this nuclear norm, right? What is T here? So with HDPROS, what we do is that we gonna look for similar patches in the images. If you have similar patches and you put them next to each other all together, you concatenate these patches, you will actually have this kind of matrix X, and you could do it easily on your own images. You would see that if you pick similar patches, you'll get a very low rank matrix with just a little bit of noise on it. And so that's exactly what we do here. The T is nothing else than a patch selection operator that works on the image that we want to recover, the image X. The little p that you see there is just the reference patch. You are going to look for similar patches, for patches that are actually similar to this patch p. But of course, you have many patches in the image, so you're going to repeat that for all pixels, all voxels in your 3D image. That's what you see on the right there. And so we minimize the rank of these similar patches. And that's basically a very efficient denoising. And I'm going to show you how it works. But before, we have to solve this equation here. And there is, so it's kind of hard to solve this equation in practice because of, problem of convexity, problem of linearity. It's really difficult, but we have a solution which is called the ADMM. And that's also something Jerome mentioned just before. The ADMM is very nice, and the goal of ADMM is to basically decompose the main optimization problem into several sub-problems that are solved in an alternating fashion. And one thing to know about ADMM is that not only it is easier to solve your main optimization problem, but ADMM also algorithm have excellent convergence properties. And so you see the trick. I have replaced the operator P here by variable T. You see, now that's the equation I'm trying to solve, and that's what we call a constraint optimization. Now we have this constraint here. This is very easily solved because now we could iterate and solve this optimization problem with regards to two variables, the variable X that we want to recover and the variable T. The great thing is that X is not in this regularization term anymore, so we can split the two optimization problem. And it becomes very easily, it's very easy to solve it now. If you want to minimize this optimization problem with regards to X, you just have to solve this term. And this is a very basic L2 norm minimization problem. And Jerome mentioned that before. You could solve that very easily with a conjugate gradient algorithm, for example. So you've solved that, you've recovered the first version of X, and then you are going to optimize the second term, which is this patch-based denoising. So now it's the denoising step that you solve. And again, this is very easily solved, and I'm going to show you how to do it. And then you update the Lagrangian. The Lagrangian is just an update on the constraint here. It's just one line of code. This is a linear update. And so you iterate these three steps for a couple of iterations. In the application I'm going to show you later, we do between 10 and 20 iterations. So very easily solved for X. For T is a higher order denoising. And how do we do it in practice? I've compiled a couple of videos for you to show you how we do this patch selection and this hard thresholding. So I invite you to try that on your images. It could be 2D multi-contrast or 3D multi-contrast. And if you follow these videos, you'll have at the very end a very good and efficient denoising. So the first step is to find similar patches. Here I'm showing you 4 3D volumes with different contrast. you have your reference patch, and very easily you look for similar patches within the image. And you can do it by measuring distances, using the L2 norm, for example, or using a mutual information. Pick the tools that you like. Once you found the similar patches, you can then very easily, you just vectorize them, right? You put all the pixels in one column and you build these matrices. So you have now 4 low-rank matrices because the patches are similar. So the only difference will be the noise. And then this is the most important part. You build a tensor out of these multi-contrast matrices. So you have a 3D tensor. You just stack the previous matrix, and this tensor is low rank. We've seen that in the previous slide. So you just do a singular value decomposition, and you keep the main singular values. Here I've just kept 5 singular values, and this really acts as a very efficient denoising. And now we're done with the denoising. We just have to do the inverse process, build back the patches, put them in the original position in the image, and that's it. And here you'll have a very efficient denoising. So you can implement that in a couple of lines in MATLAB. And believe me, this is really efficient. And you'll see the images just after. So at this step, we have optimized on T, right? We have the T that is denoise, and now we are gonna run the second optimization, which is just an optimization on the image X. And this is done with a very simple conjugate gradient, as you're used to do. And we iterate between the 3 steps, and we have this HDPROS reconstruction. So I'm gonna show you a couple of examples. The first example is for fingerprinting, 2D fingerprinting. And in this experiment, we collected 2,000 time points in a continuous acquisition by just varying the flip angle. And that's the flip angle diagram that we've used in the scanner. And we've compared the HDPROS with the conventional low rank inversion LRI that is quite established in the field. And with this application, so it was done on brain MRI, we could extract T1 and T2 maps out of all these time points images. So very quickly, just to show you on a phantom that HDPROS does not impact the accuracy of the extracted T1 and T2 values. When you compare HDPROS with the conventional and very long spin echo acquisition, you see that you do preserve the accuracy. For T2, for the high T2, we're not that accurate, but that's not a reconstruction problem, that's an acquisition issue. But most importantly, if you look at the precision, so basically the noise in the image, you clearly see on T1 and T2 that we have a better precision, we have a lower standard deviation with this application. And now look at the images you could get with HDPROS. On the left, you have the 2,000 temporal fingerprinting time points. You see that it's highly undersampled, that is very noisy. And so this denoising step, if you exploit the multi-contrast information, you can really recover a very nice image quality and sharp data sets. I'm gonna show you a second case that was a little bit more challenging. And you see on the right, for example, here for the very last time points, you on the conventional reconstruction, you really lose a lot of information. You really lose structural information that you can recover with HDPROS. So if you look at the time point 4 here, for example, by exploiting this contrast information, you can really recover a lot of information that could potentially be lost with conventional reconstruction. And this, of course, impacts the T1 and T2 maps. You have a higher SNR, you have a sharp data set. And I think since it's quantitative application, if you look at the T1 and T2 values, you do preserve the accuracy again, but you have a better precision with HDPROS. So that was the first application. The second application is for 3D reconstruction, 3D multi-contrast reconstruction. And here we don't do a continuous acquisition, but we are gonna collect 6 3D volumes with different contrast between them. And these volumes are highly undersampled, almost a factor of 7, so quite high. And this is done using this variable density sampling. It's a Cartesian sampling. You're familiar with that. The only difference is that we shift the sampling between contrast. And that's a very important ingredient of compressed sensing. And that's something Jérôme mentioned earlier. You need this random or pseudo-random acquisition. And so the goal was to reconstruct these highly undersampled volumes and compare them with a fully sampled acquisition. By the way, this was empty weighted images, so different empty contrasts between the images. So here you see one 2D slide that we extracted from the volumes with, and you see the different contrasts between the 6 images. On the top, you have the Jérôme's algorithm, the compressed sensing algorithm. On the bottom row, you have the HGProst reconstruction. And if I show you a close-up, you see that we can recover a couple of structures. And you also see, compared to the previous application, that we can really control the denoising here. I didn't push the denoising too much here. So we still have a grainy image, but still we do recover a lot of sharpness in these images. But the good thing is that we have acquired with a high undersampling factor, so it was a 6-fold acceleration. So we could really acquire 6 volumes for the same price if you compare to a fully sampled acquisition, right? For the same acquisition time, you have much more data sets. And still, again, if you look at all the contrast, you are able to not only preserve the contrast, but also to recover sharp details in each of these volumes. That was just two, there were 2 applications that I've shown you, but many people have used this algorithm for many applications. Recently, Ruud has been using it for knee cartilage imaging. Again, very similar result in a nicely denoised image that they were able to get. You could use it for almost all the mapping applications very easily. For example, for T2 mapping, Olivier Jaubert from UCL have used it for almost all his applications for fingerprinting to extract fat fraction, T1, T2, T1 row mapping. And why that? It's because it's quite easy to use this algorithm. So I invite you to check this GitHub page and download the algorithm. There's a demo file. And in just 2 minutes, you'll be able to denoise your own images. And that's more or less the conclusion of my talk. Please have a look at the website. Please use HGProst. A lot of you have been using it so far. I'm always available if you have any questions or if you have any idea of extension, because we could do it for 4D, 5D, 6D, any dimensions. So there are a lot of things to do still with this algorithm. And don't forget the workshop, of course, in 2 to 3 weeks. Thanks, everyone.
Thank you so much, Aurélien, for the great talk. And actually, I want to thank both of the speakers, because it was a really great session where we started with the basics of compressed sensing and ended up in the amazing applications that we can get out of it and out of improving these techniques. So I'm going to open the floor for discussion. So whoever has questions may ask them. If not, maybe I can start, because I do have a question, and I have a question that kind of focuses on both of you. So it's kind of great that I can get to ask the question at the same time, which is, so we have this great techniques from the basic compressed sensing equations to already adding low rank and patch-based denoising. And I look at all the equations that you showed, and I see one factor in common, which is the regularization term. And being a person that works with compressed sensing, I don't know, this is kind of a tricky question, but I wanted to ask your thoughts about how to better optimize this type of frameworks, because in any case, we are working with medical data. We want to ensure that whatever we are reconstructing is actually accurate. We are not missing like clinical details or things that could actually contribute to a good diagnosis or a good planning for the patients. And this, I think, is very much related with the way we regularize, because if we regularize too much, our images get blurred. If we regularize too few, our images get noisier. And so I wanted to hear your thoughts on that and what you are currently doing to address this type of issues.
Leon, you want to start?
I'll start very quickly. I think it's a very good question. Partly, if you so if you've used compressed sensing, so like TV or wavelets, you would soon realize that when you start increasing the acceleration factor above 3 or 4 and push the regularization, TV will fail on the flat areas, for example, blood pole or myocardium wall, because the contrast is so similar that at the end TV will just give one, to exaggerate, one single value to these regions of the image. With patch-based, it's a little bit different, because here we're really focusing on the structure, right? And so what we've seen, and we've compared with ground truth and the application I've shown you, we had a fully sampled acquisition. We could make sure visually that we do preserve this information. We don't smooth too much. We preserve the sharpness. But of course, with any optimization problem, Mariana, you'll have to be careful with this regularization parameter. You'll have to tune it very well on many data sets. But my conclusion is just, it's way easier when you use patch-based regularization, because you're really into the structure of the image.
And something that goes along what Aurélien just said, we've noticed as well that those regularization parameters a long time, for example, when you try to measure the ejection fraction, it's a big issue, because if you want to improve the image quality, you increase the regularization weights, but at the same time you will compress the motion, and then you will underestimate the ejection fraction. But no, so the work from Bastien and Chris has shown that by including motion fields in the reconstruction, you can get around this issue as well. So it's kind of like Aurélien said, you focus more on the structure instead of on the image quality. But yeah, but that's a big issue, and if a lot of people have tried to find a good solution for this lambda, and so far it's just like a trial and error, I think.
And in that same thought, for instance, the patch size, how is that influencing as well your reconstruction quality, and how can that improve or reduce the quality of the images that you obtain?
Yeah, that's a good point. So the patch size is just related to the resolution of your image. And you can check the 2 papers I've published on POST and HDPROST. You could very easily find the size of the patch based on the resolution, right? Low resolution, you'll go for very small patches, 3 by 3, for example. Higher resolution, and for sub-millimeter resolution, it will be around 10 by 10. So everything is really fixed, and you can find that in the paper. So it's not too much trouble to find this parameter.
Okay, thank you so much to both of you. Is there more questions in the audience?
I don't have a question, but just to speak about the last question. First, thanks to Jérôme and Aurélien. It was great to have a talk with a clear explanation on these topics. It's really funny, because when you publish a method, you have to explain a lot why you pick a kernel of 3 or 5. But at the end, now no one speak about the size of the grappa kernel. It's not a discussion. Someone fixed it, and it's always used. So maybe it will be the same for the HDPROST in the future.
Yeah, that's a good point. Yeah.
I see we have a raised hand as well. I don't know if it's to ask a question or to join the discussion.
Can you hear me?
Yes.
All right.
Yes.
First of all, thank you to the both of you. That was awesome. Very nice explanations. Even I could understand most of it. However, I have one question for Jérôme in that context. And if you showed your square that was tilted to the side by 45 degrees there, I think it was an L1 norm. You know, why go through the pain? You just put one coefficient to 0 and you're done.
I'm not really sure if I know which image you referred to.
You have this line like with M1 and M2.
Yes.
And first you show a little bubble that where you find the combination, and then you turn a square on the side.
Yes.
And this touches the line where I think M1 is 0.
Yes.
Fine, but why go through the pain with this square where you could put M1 to 0 everywhere?
Well, you don't know which one. You don't know if it's M1 or M2 that has to be 0. So, I mean, you cannot just start randomly set some coefficients to 0. I mean, you really need, I mean, basically that line, the line you saw, it's really, if you travel along that line, these are all possible combination of M1 and M2 that are possible. But the only 2 points where basically it crosses, I mean, in this case, there were only 2 points where one of the coefficients was 0. And the one that was basically the closest to, I mean, giving you the minimum L1 norm was the one where you have the line crossing the M2 axis. I don't know if you remember that. I mean, the other one, if you were to set the other one to 0 by mistake, it means that basically you will L1 norm is much bigger, so it is not as sparse as the other one.
Okay, great. I get it now. And then I have a question for Aurélien. Just as a reality check, if you choose your patches to be the size of a voxel, what happens?
Then you are doing what we call the low rank inversion. You are just gonna exploit the contrast dimension. And you've seen on the images for fingerprinting, for example, that's not enough. You would lose a lot of structures, particularly when it's highly undersampled. So in my case, was the very last time points. If you now have a patch, so a patch size higher than 1, you are adding more information, more correlation information by picking all these patches.
Right, but I mean, okay, the smallest patch is 1, that's probably no good. The biggest patch is as big as your
image.
Your image, that's probably also no good. So
that's multitasking.
So it comes back to the question of Mariana, I think. So with the lambdas, you know, what's the optimal size?
Yeah, that's exactly what I said. So this size is related to the resolution of your image. And that's something you'll have to do. So if you want to play with this code online, you will have to figure it out. You know the resolution of your image, so you will just have to change this patch size accordingly. Bigger patch size for higher resolution. That's a very simple exercise, and it takes less than a minute, Matthias.
Okay. Thank you very much, both of you.
I have a question for you, Aurélien, as well. So with your maybe can you just mute the Lausanne's room? Because I can hear myself back. So when you select your patches, you basically select your patches, you do your singular value decomposition, you threshold your singular values, and then when you place your patches back into the image, I've started thinking, what happens if you have different patches in your image that share the same patches? So if you start replacing the same patches over and over, so what happens? I mean,
that's great.
That's okay.
Yeah, that's great. Actually, it's even better because you've denoised the same pixels multiple times, right? So what we do is called aggregation. You basically do an averaging of all these denoise patches, right? So I like to have a little bit of overlap, actually.
Okay.
That's a parameter you fixed in the algorithm. If you check the code, you'll see that. It's called offsets.
Yeah.
It's how many pixels you will skip during this patch selection. So if you want to do many overlaps, it's even better. The only problem is that it will take longer to perform the denoising because you have many similar patches to find.
Okay. Yeah, I remember seeing that. It's true.
Mhm.
Okay.
But maybe one thing for everybody that is here today, I really invite you to check Jérôme's code on compressed sensing or TV or patch-based denoising. Everything is online, and it's very easy to use it for your own application. So if you have single contrast or multi-contrast application, just run the demo file, and you'll get denoise images very quickly.
Thank you so much to both of you and for the questions. Do we have more questions from the audience? We have muted Ruud.
Yeah, I was still sorry about that. Then I turned on my video, that didn't help much. So a quick question for either of you. So we often see now indeed this discussion about the Lambda optimization and so on. Recently, I've heard a lot about needing to adapt the sampling to the reconstruction that you want. Can either of you comment on that? That you shouldn't just sample your random variable density semi-random thingy, but you should actually adapt the sampling to the reconstruction that you want. Is that really a thing that that needs to be added to either of your frameworks, or is that not really relevant in this setting?
I think okay.
Sorry, go ahead.
I think it's extremely relevant, and that's something Bruno Tesson has been mentioning to me for a couple of years. That will help the reconstruction for sure. I've never done that, but I'm pretty sure that's something that will help. I don't know if Jérôme, if you've done that before.
Well, I mean, I don't know at what point you want to tailor the acquisition, but I mean, the acquisition should always be tailored to the reconstruction. So depending on which reconstruction you want to use, you need to design your acquisition so that it fits your model. For example, if you want to do GRAPPA, you have to fully sample the center so that you can calculate your kernels and stuff like that. So for compressed sensing, it's always, of course, you need sparsity, you need the randomness, but then you still have to sample the center because that's where all the information is. So it's always a trade-off. But then you can, probably even further optimize this acquisition to get even better reconstruction. But I haven't really looked into that, to be honest.
Thank you.
Thank you so much, Ruud, for the question. Do we have any other questions for the speakers or for discussion for everyone?
Maybe one thing to add on your question, Mariana, about this lambda parameter. I'm not a big fan of, as a mathematician, I'm not a big fan of deep learning tools for reconstructions, but deep learning could help here. If you've seen the recent papers, you could learn the optimal lambda using a smart deep learning reconstruction. That could be one solution.
I agree, but I do think it is still a bit tricky. I don't know. I always wonder regarding the consequences that has to the actual image quality. We are still, once again, handling patient data, and we want to ensure that whatever we are doing is corresponding to the ground truth.
Yes.
So for sure, in that sense, I think deep learning would be more useful than, for instance, the applications for image reconstruction directly, that I must admit I don't really trust right now. But I think it would be very interesting to also try it, for instance, in our free running data set. Well, thank you a lot, guys. I don't know if there's any other questions that I can just do one last shout out for questions, I guess. We have
maybe I can ask one to Jérôme.
Yeah, of course. Well,
it's a tricky one.
Time.
Thanks, Aurélien.
And I'm not sure you have the answer, but compressed sensing is quite old, right? What is it, 10 years old, 10, 12 years old? At least the application to MRI.
Oh, yeah, okay.
Why did it take so long to have that implemented as a product with Siemens, and why it's not implemented with GE yet, even though Mickey Lustig have started working closely with GE? Do you know why it took so long?
That's a good question. I mean, I think if I remember correctly, his paper was from 2007. I mean, Mickey Lustig's paper, if I remember correctly. So it has been many years. It's true that I always thought that GE will be implementing compressed sensing very quickly because, as you said, Michael Lustig was working for them. but I have no idea why it's taking so long. I think it could be just like, I mean, on the Siemens side, I know that they can only do 2D reconstruction with compressed sensing just because the computer is not powerful enough. So it could be that, but I don't know. I think we lost Aurélien.
Maybe.
It's not moving
Yeah.
anymore on my screen.
Yeah, it's not moving on my screen either.
Okay.
But I don't know. In my opinion, I think it could also be related to the translational side. So I think it's just harder to add new techniques for imaging, and this could be one of the factors.
Yeah. Yeah,
But,
it's a good question, but I don't know, to be honest. I have no idea. It has to be validated, I guess, first.
We have
Yeah.
Lausanne comments as well. Sorry,
When you do,
go ahead.
when you ask, sorry, when you ask for FDA approval of a new product, you have to show that's equivalent to the previous one. So you need to, at least Siemens has done this compressed sensing whip quite early, as far as I remember. And then it took some years to validate and have the data to submit to FDA and to all these things. I have no idea why G wouldn't. I mean, I remember a couple of ISMREMs ago, Mickey Lustig doing the lunch talk at G and clearly saying, why didn't you implement it yet in the product, sort of, in the G lunch symposium? So I don't know, I think this is part of it. Part is definitely computer power, so you cannot put something at the scanner that takes 10 minutes to reconstruct. That is not something you want to do. So you need to bring it down to clinical reconstruction times. But then for 2D now with the GPU, they can do it. And the other part is the validation. You need to submit equivalence to FDA and to the European. So it takes time. I don't know, we should maybe check how long it took from the Grappa paper to the product Grappa. It might be a similar time frame. And the same for fingerprinting. I think that will have to be validated as well.
Yeah. Grappa wasn't too long. Yeah? Grappa was first published, what, in 1999? So, and it came product quite early.
Yeah.
2000.
Multi-band acquisition was also super fast to be used in the clinic.
Then I don't know,
Matthias?
I guess, yeah.
Sorry, go ahead, Davide. Sorry, I just want to.
No, then I don't know, might be indeed
Mhm.
more connected to reconstruction times as well.
Yeah. I think the group in Lausanne has a question too.
Yes, you're muted.
I have a comment to that GE story. I mean, it already took them 10 years to catch up with parallel image to Philips, right? Who was the first. So there they were sleeping. They simply didn't have the hardware to do it. Here, I don't think it's the same reason. I was at the booth of GE and talked to them a little bit, and really they put an emphasis on AI for reconstruction on the one hand, on these blanket coils on another hand. So I think they're making progress in different domains. They just, chose to put an emphasis on some other aspects than the other companies, which is of course okay. And we will see whether, the success gives them right or not.
I just got a message from Aurélien. He says that there's a big power outage in Bordeaux. So
Yes, we also got information in the chat.
Oh, I did as well.
this.
Okay.
So I think they might have some troubles reconnecting due to the power outage.
Yeah, I'm connected through my mobile. Otherwise, I think the Wi-Fi server is off.
Mhm.
Cool. Thank you, Mariana.
Well, thank you guys for the great discussion and great comments and lots of things to think about in the future. Considering we have a power outage on the Bordeaux side, I think this is a good moment to close our session for today. I would just like to mention to everyone that in case you are interested to watch this session again, or even send it to someone who might find this session insightful, this session will be available on the Lyric website that I would have provided you with the link, but it was Aurélien who was in charge of sharing the link with everyone, and I don't have the link with me. But go to the Lyric website and you'll find out where these sessions are recorded. Well, thank you a lot. It was a really, really great talks. Thank you, Jérôme, and thank you, Aurélien, for teaching us a little bit more about what you are working with. And thank you everyone for the discussion.
Thank you. Bye-bye.
Before, sorry, I just want to say, save the date for the 17th of June, where it should be the next Cardiac Imaging Journal Club. That's just it.
Thank you.
Thank you.
Bye.